So this is the third and final video on graphing exponential growth or decay functions. And again, you have all these notes, very important notes. Please take the time to pause the screen and read them all and understand them. Let's jump to some more graphing. And I'm going to the back side of our handout that was given to us on Monday, which is dealing with exponential decay functions, which we already know that exponential decay functions have a base that's less than 1. Anyway, we have this very basic type of exponential decay function. We've already done that in class, so let's jump to something more interesting, kind of like this one right here. Anyhow, how do we work on this graph right here, this exponential decay function? Well, let's all start off by doing a XY table, okay? And let's plug in some consecutive integer inputs. Like let's put 0 in the middle, and then 1, and then 2, and then 3. Let me make this darker. There we go. And let's also go -1, -2, and so on and so on. If we need more, we'll plug in more. But for right now, let's take the 0, plug it in, which means that that becomes 1, which means that the A value is the output. So in this case, we have an 8 when we plug in 0. Now, what could we do from here? We could plug in the 1 into the x and work it out, but the easier thing to do is to look at the base, which is 1/4, and that's how we're going to get from this output to the next output, by taking 8 and multiplying it by 1/4. Now, right here in blue ink, I'm just showing you what I'm going to be doing here, times 1/4. So if I go 8 times 1/4, it's really going to be 8/4. And 8/4 really is 2, okay? So when I do plug in 1, I get out a 2. Does that make sense? I hope so. So if you keep multiplying by 1/4, because that's what the base is telling us to do, to multiply it by 1/4. If I do take the output 2 and multiply it by 1/4, think about it right here on the side, 2 times 1/4, we'll put the 2 over a 1, that'll give us 2/4, and what does 2/4 reduce down to? It reduces down to 1/2. So I'm going to put 1/2 right there. And if I multiply 1/2 again, the output 1/2 times 1/4, because that's the pattern, the base tells me what to do as I go down on the outputs. And this is only because the inputs are in order, okay? So 1/2 times 1/4, again, I'm going to show my work right here in blue, times 1/4, that's going to give me a 1/8 as an output, 1/8 as an output. So all these are coordinates, and to tell you the truth, we don't even need these guys because we already know it's approaching 0. Now going in the opposite direction would be doing the reciprocal of 1/4, which is times 4, okay? So think about this. Instead of 8 times 1/4 to give us 2, we could go 2 times the reciprocal of 1/4, which is 4. 2 times 4 gives me 8. 8 times 4 is going to give me 32. 32 times 4 is going to give me 128, I believe. And again, we're not even going to use these ones over here because the graph is only a 10 by 10 graph. So let's plot some points. So let's do 0, 8. 0, 8 is way up here. And let me put that as a red dot way up here. And let's go to 1 and 2, the coordinate 1, 2. So if I go to 1 and 2, I'm right here at this coordinate. And if I go to 2 and 1/2, because that's the next coordinate here, 2 and 1/2. 2 for x, so I'm at 0, I go 1, 2, and then halfway up. Let's put a dot right there. 2 and 1/2 is halfway up. Whoa, that's not exactly right. Let's just put a dot right there, halfway up. And we know that as this thing goes from left to right, it's going to approach 0, okay? Because 1/8 is even smaller than 1/2. Let me show you what I'm talking about. Right here we're at 1/2, and then the next one's going to be 1/8, and then the next one's going to be 1/16, and so on. It gets smaller and smaller and smaller. You're not going to even be able to show that difference. So what we're going to do is simply draw like if it were on the x-axis itself, even though we know it never actually touches. It just infinitely approaches. And the reason why I'm drawing this, the reason why I know I'm done, is because this original exponential function, or let's correctly say this original exponential decay function, because it's less than 1, does not have a h or k shift, so I don't have to worry about moving the dots 1 to the left or 2 to the left and 5 down or anything like that. I don't have an h or k shift, so I just graph it, I'm done. Let's go to something that does have a h or k shift. Let's do this last one right here. Or, let me check out this one up here. Well, we could either do that one or this one. I'll go with the bottom one right here. So, if I want to graph this one, again, go to an XY table. But before starting to figure out points, we need to identify h and k. H is -1, and how do I know that? H is always with x, and you have to think opposite. So if there's a +1 right here, h is actually -1. And what that means is it's going to be a movement of 1 unit to the left, okay? And the k value, you always take it for what it is, right? Is -3. So the k value is -3, that means it's going to go down 3 units at the end of it all. So how do we graph these guys once again? You have to kind of ignore h and k, so it's kind of like ignoring h and k and focusing in and creating a x and y table based on your parent function, ignoring h and k, okay? So once again, you could put 0, 1, 2, 3, -1, -2, and so on and so on. If you do plug in 0 right here, it gives you just the a value of 3. So we're going to get out of 3. If you plug in actually don't even plug in anymore. Now you could just think of your fraction, which tells us that I need to take 3 and multiply it by half, and that will give us 3/2. And if I take 3/2 and multiply it by half again, it'll give me 3/4. And if I take 3/4 and multiply it by half again, it'll give me 3/8, right? Now going backwards, instead of multiplying by half to get to the next one, going backwards would be multiplying by the reciprocal of half, which is really 2. So this times 2, this times 2, this times 2 gives us 3. 3 times 2, which would be right here, will give us 6. Times 2 will give us 12. And those are all the coordinates that we need. Let's go to the coordinate 0, 3. 0, 1, 2, 3 is right here. There's the coordinate 0, 3. Sorry, it's a little bit off. And if we go to the next coordinate, 1 and 3 halves, think about this coordinate right here, 1 and 3 halves, that's really 1 and 1.5. So if I go 1 and then 1.5, that would be right in between the 1 and the 2. If we go to 2 and 3/4, think about that. You're at the origin and you go 1, 2, and you go 3/4 of the way up. It's not even all the way to 1, it's below 1. And if we go to the -1, 6, this coordinate right here, -1, 6, well, if you go to -1 and 6, it's going to be -1 and 1, 2, 3, 4, 5, 6, going to be right there. So there's -1, 6. And of course, if you went to -212, you'd already be off the graph. -212 would be up here somewhere. Okay, so we know that this is decaying, and it looks like it's curving, and it's going to decay to 0, to nothing. So I'm going to already draw my end part of my graph as if it were on the x-axis, even though we know it never actually touches, just infinitely approaches. Now, I'm not going to draw a line through this one. Why not? Because this is not my graph, not my real graph. Because I still need to take into consideration my h and my k to graph the whole thing, not just the parent graph. So I need to take every single one of these coordinates and move them 1 to the left and 3 down. Okay? So if I do that with all of these guys, let me show you. I want to take this guy and go 1 to the left and 1, 2, 3 down. And if I go to the next one, go 1 to the left and 1, 2, 3 down. And if I go to the next one, which is in the halfway point, if I go 1 to the left and 1, 2, 3 down, it's at the halfway point right there. And a very easy one to do is to actually move your asymptote, the last part of your graph, which is touching your asymptote, or at least it looks like it's touching the asymptote, and move that 3 units down. Remember, your k always gives you your new asymptote, -1, -2, -3. So let me draw it right there. And let me connect these dots. And ladies and gentlemen, we have our exponential decay function completely graphed right here. And that is considering the whole thing, the whole function, including your h and k, not just your parent graph. So if you do this on a test, I recommend you put two x's on the graph that's not your final graph. That first one was just a parent graph to be able to get to the final graph. Now, of course, you could actually avoid all this h and k shift if you actually wanted to plug in, like you could actually plug in 0 if you wanted to into the whole thing. Plug in 0 right here, you're going to get 0 plus 1, which is a 1, right? And if you go 1/2 to the 1 power, that's 1/2, and then 1/2 times 3, well, that's 1.5, and then 1.5 take away 3, that's going to give me a negative 1.5. Yeah, it does get a little confusing, but if you think about it, that is a coordinate on the final graph. 0 and negative 1.5, you get to that black dot right there on the final graph. The problem with that is, man, you got to do a lot of math to get all of the coordinates on that final graph that you see here. I think it's a lot easier to identify h and k, and then ignore h and k by just focusing in on your parent graph, making an XY table for it, using the pattern that you see to get your outputs instead of doing a bunch of math, plotting those points, getting your parent graph, and then moving it according to h and k. I hope this helps. Please post if you guys have any comments.